The last light of the outer planets fades slowly into the endless black. Beyond Neptune, the sun is no longer a blazing sphere, but a pale ember, a coin of fire that casts a thin, silvery light across a realm of frozen giants and drifting ice. The temperature falls to nearly absolute zero, where the faint warmth of the sun is little more than a whisper across the cosmic dark. For a long time, humanity believed that this was the edge, that Pluto marked the final frontier of our solar dominion. But the truth is far more complex and far more profound. The solar system does not end with the last planet. It stretches trillions of kilometers outward into a vast unseen ocean that few ever imagined. If we could ride on a beam of light and look back, we would see the entire solar system shrink behind us. The planets would fade one by one. Jupiter would vanish first, then Saturn, then the blue gems of Uranus and Neptune. Beyond them, Pluto would drift in slow silence, its orbit tilted like a forgotten shadow. And yet even beyond Pluto, the influence of the sun continues, shaping and defending an invisible frontier. This boundary is called the heliosphere, a colossal bubble carved into the interstellar gas by the solar wind. The solar wind is a river of charged particles, mainly protons and electrons, that flows outward from the sun in all directions. It moves at hundreds of kilometers per second, carrying with it the magnetic breath of our star. This breath inflates a vast cocoon around the solar system, protecting it from the high-energy radiation of the galaxy. The heliosphere is not an empty shell, but a living boundary, constantly sculpted by the sun's changing moods. When solar flares erupt or magnetic storms burst from the surface, waves ripple outward through this immense bubble, echoing across billions of kilometers. The inner planets live well within this sphere, bathed in the constant hum of solar wind. But as one travels outward, the strength of that wind weakens. Somewhere far beyond Pluto, the solar wind begins to slow and thicken as it collides with the thin gas between the stars. This is the first sign that the solar system is approaching its true edge. Scientists call this region the termination shock. Here, the solar wind slows abruptly, compressed by the resistance of the interstellar medium, and its temperature rises dramatically. Beyond the termination shock lies the heliosheath, a turbulent layer where the solar wind and interstellar gas wrestle for dominance. The existence of this region was only confirmed through the courage of two ancient explorers. In the year 1977, NASA launched twin spacecraft on a mission that would change our understanding of the solar system forever. Voyager 1 and Voyager 2 were designed to fly past the outer planets and then continue onward into the unknown. They carried golden records, time capsules etched with images, sounds, and greetings from Earth, intended for any beings that might one day find them among the stars. What began as a planetary tour soon became a journey to the very boundary of the sun's influence. As the Voyagers traveled outward, they passed through the magnetic and particle fields of the giant planets. Voyager 1 swept past Jupiter and Saturn, while Voyager 2 ventured farther still, visiting Uranus and Neptune before heading toward interstellar space. Their cameras captured the faint blue arcs of Neptune's atmosphere, the stormy bands of Jupiter, and the golden rings of Saturn that glowed like frozen music. When their cameras were finally turned off to save power, they continued as blind messengers, carrying our presence into the void. By the early years of the 21st century, Voyager 1 had reached the outermost reaches of the heliosphere. In 2012, it crossed a boundary that had only existed in theory: the heliopause. The heliopause is the point where the solar wind ceases to push outward and the pressure of the interstellar medium begins to dominate. Beyond it, the sun's magnetic field weakens into the great cosmic sea that fills the space between stars. It is not a sharp line, but a turbulent frontier where magnetic waves collide and twist, forming a stormy layer of energy. Voyager's instruments recorded sudden changes in particle density and direction, confirming that it had entered interstellar space. the first human-made object to do so. For centuries, we imagined interstellar space as a perfect void. But the data from Voyager showed something richer and more complex. Even in the great darkness between stars, there is matter. There are atoms of hydrogen and helium, dust grains, and the faint echo of ancient supernovae scattered across unimaginable distances. The interstellar medium is thin beyond comprehension, far emptier than any vacuum we can create on Earth, yet it is also the birthplace of everything. From this cold ocean of gas and dust, stars are born, and planets form around them. Standing at the edge of the heliopause, Voyager 1 now drifts through that frontier, over 20 billion kilometers from home. Its signals, traveling at the speed of light, take over 20 hours to reach Earth. Its power slowly fades as its plutonium generators cool. Yet it continues to whisper back across the dark, carrying the heartbeat of a civilization that once looked up at the night sky and dared to reach beyond it. Voyager 2, following a different trajectory, crossed the heliopause 6 years later, confirming that the sun's bubble is not symmetrical but shaped like a comet, elongated by the flow of the galaxy around it. What these two travelers revealed is that the solar system does not end where light fades or where planets stop. It ends where the wind of the sun can no longer hold back the pressure of the galaxy itself. Beyond that boundary lies true interstellar space, a place that belongs not to any one star, but to the universe as a whole. In this way, the edge of the solar system is not a line but a threshold. It is where the light of one star meets the dark sea that connects all others. Beyond that sea, the galaxy itself awaits, filled with billions of suns, each surrounded by its own unseen frontier. As Voyager drifts onward into this interstellar expanse, it carries with it not only the data of plasma waves and magnetic fields, but a deeper message that boundaries are illusions born of distance, and that every end is only a doorway to a greater beginning. The outer planets fade behind us. The sun dwindles to a star among countless others, and what once seemed like the edge of everything we knew becomes the threshold of the infinite. And yet, somewhere in that silence, the signal still pulses. It crosses the void, faint but steady, a heartbeat of human curiosity echoing across the cosmos. It reminds us that the edge of our solar system is not the end of our story. It is the beginning of our understanding that space has no true boundary, only deeper mysteries waiting to be seen. If we could ride alongside Voyager 1 now, it would appear as a small metallic insect adrift in an ocean of darkness. Its golden antenna glints faintly in the weak light of distant stars, spinning slowly as it sends its ancient signal back toward Earth. Around it stretches a silent expanse, a boundary between two cosmic winds, the one that breathes outward from the sun, and the one that flows inward from the galaxy beyond. Here, in the Helios Heath and beyond, the fabric of space itself feels different. The density of charged particles rises, the magnetic field shifts direction, and the temperature of the plasma reaches tens of thousands of degrees Celsius, though the gas is so thin that a human hand would feel nothing at all. When Voyager crossed the heliopause, it entered a region of pure interstellar material. This is not emptiness, but a thin fog of atoms and ions that fill the galaxy. Each cubic centimeter may hold only a single particle of hydrogen, but over the vastness of light years, those particles become a living ocean. They carry whispers of long-dead stars, the debris of supernovae, and the chemical seeds from which new worlds will one day form. This invisible medium binds the galaxy together, linking every star in a continuous web of matter and magnetism. Scientists often describe the heliosphere as the sun's protective bubble, a shield against the violent radiation that pervades interstellar space. Cosmic rays, high-energy particles born in the explosions of distant stars, stream through the galaxy at nearly the speed of light. The heliosphere deflects most of them, bending their paths away from the inner planets. Without this shield, Earth's atmosphere and life itself would be bombarded by far greater radiation. The faint hum of the solar wind, though gentle, is what allows life to exist in peace beneath the sun's warm glow. The edge of this bubble, however, is not static. It breathes. When the sun grows, more active, the heliosphere expands, pushing outward against the galactic flow. When the solar wind weakens, the boundary retreats. Over the course of the 11-year solar cycle, the heliopause can move inward or outward by billions of kilometers. It is a living frontier, constantly shifting in response to the pulse of our star. Voyager's data reveal these fluctuations in exquisite detail, showing that even at the edge of the solar system, the heartbeat of the sun can still be felt. To imagine the scale of this structure is to confront something nearly beyond comprehension. The heliosphere extends well beyond the orbits of the planets, perhaps 150 billion kilometers in radius. Beyond that lies the Oort cloud, an even more distant region where trillions of icy bodies circle in darkness. But even that immense domain represents only a faint glow within the Milky Way. To the galaxy, our solar system is no more than a speck of dust drifting in a sunbeam. As Voyager continues its journey, it passes through waves of magnetized plasma that ripple like unseen tides. The magnetic field here is not random. It aligns with the broader structure of the galaxy, tracing lines of force that stretch between the stars. These fields guide cosmic rays, shape the flow of gas, and influence how stars form and die. Voyager's instruments, though aging, still detect subtle variations in these fields, helping scientists map the invisible scaffolding of the Milky Way. Every signal from Voyager takes more than 20 hours to reach Earth. Each piece of data is precious, a final whisper from a spacecraft that has traveled farther than any before it. Its power is fading. By the mid-2030s, its generators will fall silent. But even then, Voyager will continue onward, coasting among the stars for billions of years. Long after humanity is gone, it will still carry its golden record, a message to the cosmos, inscribed with greetings in 55 languages, music from Bach and Chuck Berry, and the sound of a human heartbeat. It is a testament that somewhere in the universe, there once existed a species that sought to know its place among the stars. The heliosphere, vast as it is, represents the last breath of the sun's influence. Beyond it, the interstellar medium takes over, a realm that belongs to no single star. Yet this transition is not a simple line. It is a meeting place of forces, a region where the solar wind meets the galactic wind, where particles from two different realms mingle and exchange energy. Some scientists liken it to the foam on the edge of a wave, a turbulent froth where the boundaries blur and vanish. As we move farther out in imagination, the sun becomes just one star among hundreds of billions. Its light grows fainter until it merges with the pale haze of the Milky Way. The heliosphere fades behind us like a glowing bubble lost in the sea of space. And yet, it is within this fragile bubble that everything we have ever known exists. Every planet, every moon, every spark of human life. To understand its boundary is to understand how small we truly are and how extraordinary it is that we can even ask where that boundary lies. Voyager's crossing of the heliopause was not merely a scientific milestone, it was a philosophical one. For the first time, something made by human hands left the domain of our star and entered the galaxy beyond. It was as if a child had stepped off the porch and taken its first step into an endless forest. The meaning of that step cannot be measured in kilometers or years. It is measured in courage, in curiosity, in the refusal to accept that the known world is all there is. Beyond the heliopause, the instruments aboard Voyager detected the faint hum of plasma waves vibrating through the interstellar gas. These vibrations revealed that the space beyond is not silent, but alive with energy. They pulse like the breath of the galaxy, a reminder that even the void between stars is part of a vast, dynamic system. Each wave carries information about density, temperature, and magnetic strength, helping us understand the environment into which our solar system is moving. For our sun and its planets are not stationary. They travel through the galaxy at tens of kilometers per second, orbiting the galactic center once every 200 million years. As the solar system moves, it drifts through different regions of the interstellar medium, sometimes denser, sometimes thinner. The shape and size of the heliosphere change in response, adjusting to the cosmic weather of the galaxy. One day, millions of years from now, the solar system may pass through a cloud of denser gas, compressing the heliosphere and altering the amount of cosmic radiation that reaches Earth. In this way, even the climate of our planet is linked to the grand dynamics of the Milky Way. When we think of the solar system, we imagine the planets, the moons, and the sun itself. But the true solar system is far larger. It is a vast, living bubble moving through interstellar space, its boundaries constantly shaped by forces beyond our sight. The edge of everything we know is not a wall, but a breathing frontier, an interaction between star and galaxy, between our small home and the infinite beyond. And out there, in that faint and distant sea, Voyager still travels. Its antenna points homeward, locked on a pale blue dot that glimmers faintly against the darkness. That tiny world, so fragile and luminous, is the source of every question we have ever asked. And as long as Voyager's signal continues to cross the void, it will carry those questions onward, proof that somewhere in the universe there are minds that dared to wonder how far the light of their own star could reach. The idea of an ending has always haunted human thought. Every map, no matter how vast, once had its edge marked with uncertainty. The old explorers of Earth once feared the horizon, believing that beyond it lay a fall into nothingness. Today, the same fear and wonder echo in our search for the edge of the solar system. Yet, what the Voyagers have revealed is that there is no cliff, no wall, no final line where the sun ends and the universe begins. There is only a gradual blending, a cosmic dusk where one realm fades into another. From the heliopause outward, space becomes truly interstellar. Here, the gas between stars forms a tenuous web that stretches across the Milky Way. The density is so low that a cubic meter might contain only a few atoms. Yet, on galactic scales, those atoms create the raw material for new stars. Over millions of years, gravity gathers them into dense clouds that cool, collapse, and ignite, giving birth to suns much like our own. In this way, the space beyond the solar system is not an empty graveyard, but a nursery of creation. Voyager's sensors, though primitive by modern standards, continue to send back faint data that reveal the structure of this vast medium. It detects variations in plasma density, sudden surges in cosmic rays, and changes in magnetic orientation that hint at unseen currents of galactic energy. Each fluctuation tells a story of the environment surrounding our solar system, a story of motion, collision, and slow cosmic evolution. The boundary that Voyager crossed is not fixed in space, but travels with the solar system itself, an ever-moving bubble drifting through the galaxy's grand ocean. Even as these spacecraft move farther away, their legacy continues to guide new missions. Future probes, equipped with more advanced instruments, will one day follow their path and map the outer heliosphere in greater detail. They will measure the strength of the interstellar magnetic field, the composition of cosmic dust, and the delicate balance of forces that define the solar frontier. In doing so, they will help us understand how stars interact with their galactic environment, a relationship that determines whether life can arise on the planets that orbit them. What lies beyond the heliopause, then, is not only the physical boundary of the sun's influence, but also the symbolic edge of human understanding. It is the line where curiosity begins to reach beyond the known, where our instruments extend our senses into realms we can never visit in person. When we speak of the edge of the solar system, we are also speaking of the edge of imagination, the point where data ends and wonder begins. In the silence beyond the heliopause, there is no sound, no wind, no visible light to mark direction. Yet even here, there are signs of movement and structure. The interstellar medium is stirred by shockwaves from ancient supernova, by the motion of nearby stars, and by the invisible gravity of dark matter that threads the galaxy like a cosmic skeleton. Every particle that drifts through this space carries the memory of a star that once lived and died. The atoms of hydrogen and helium that flow around Voyager now were forged in the first moments after the birth of the universe itself. In that sense, the spacecraft is not merely leaving the solar system, it is rejoining the matter from which all things were made. The scale is almost impossible to grasp. If the distance between the Sun and Earth were reduced to the width of a single coin, the heliopause would lie several meters away, and the nearest star would be thousands of kilometers distant. To travel from the Sun to even the closest star at Voyager's speed would take around 75,000 years. Time, in this region, ceases to have the meaning it does on Earth. The spacecraft moves through a realm where centuries pass like seconds, and the distances between stars stretch beyond the reach of comprehension. And yet, within that unimaginable vastness, there is a quiet connection. Every photon of sunlight that has ever escaped the solar system continues its journey through the interstellar dark, traveling endlessly outward. Some of that light may one day pass through the atmosphere of another world, perhaps warming the surface of a planet orbiting a distant star. In this way, the Sun's presence extends far beyond its physical influence, reaching across the galaxy in the form of light. To gaze beyond the solar system is to recognize that we are part of a continuum, not an isolated world. The same atoms that compose our bodies were once part of ancient stars that burned out billions of years ago. The same magnetic fields that shape the heliosphere also weave through the hearts of distant galaxies. The solar wind that shields us from cosmic radiation is itself a small echo of the processes that govern the universe at every scale. The boundary of the solar system, therefore, is not a limit, but a reminder that everything is connected, from the smallest grain of dust to the largest galactic cluster. When future generations look back at Voyager's journey, they may see it not as a simple scientific expedition, but as a moment of awakening. It marks the first time our species reached beyond the protective shell of its parent star and touched the raw material of the cosmos. The data that Voyager sends is more than numbers and graphs. It is a mirror held up to the universe, showing us what lies beyond the cradle that nurtured us. One day, far in the future, the Voyagers will be silent. Their transmitters will go cold, their instruments will freeze, and their golden records will drift through the dark like forgotten relics. Yet even then, they will continue to exist, moving forever through interstellar space, bearing the story of Earth. Perhaps, in some unimaginable future, another civilization will find them and decode their message. They will learn of a small world orbiting an ordinary star, where beings once looked upward and asked what lay beyond the edge of everything they knew. The answer that Voyager carries is not one of finality, but of continuity. The edge of the solar system is not the end of the Sun's domain, nor the limit of human reach. It is a passage, a doorway into the greater universe that surrounds us. Beyond it lies the interstellar medium, the galactic wilderness, and eventually, the infinite web of galaxies that fill all of space. As the faint heartbeat of Voyager fades into the noise of the cosmos, it becomes clear that this journey has never truly been about distance. It has been about perspective. From the smallest orbit to the vastest void, everything is part of a single, unbroken whole. The edge of the solar system, the heliopause, and the darkness beyond are all parts of one vast story, the story of matter, motion, and the eternal search to understand. In the end, the question of where the solar system ends is less about geography and more about perception. It ends where our influence fades, but our curiosity continues. The outer darkness is not emptiness, but invitation. The universe is not something outside of us. It is what we are made of. And so the edge of everything we know is not a barrier at all. It is a beginning, written in starlight and carried forever by the golden messengers we sent to find the truth. they are still out there, two faint glimmers of metal moving through the deep, far beyond the last whisper of the solar wind. Each day, they drift a little farther from the sun, falling outward at tens of kilometers per second, propelled by nothing more than inertia and destiny. Their names are Voyager 1 and Voyager 2, the twin explorers launched in the year 1977, and together they have rewritten our understanding of where the solar system truly ends. When the rockets first ignited beneath them, few imagined that they would still be traveling nearly 50 years later. They were designed to visit the outer planets, Jupiter, Saturn, Uranus, and Neptune, during a rare alignment that happens only once every century and 3/4. The engineers who built them could not know that the spacecraft would outlast nations, presidents, and generations. Yet they did, and in their endurance lies a story greater than any map could hold, a story not just of planets and moons, but of humanity itself reaching beyond its own cradle. Voyager 2 was the first to rise from Earth's gravity well, a silver and gold messenger launched on August 20th, 1977. 16 days later, its twin followed, riding the flames of another Titan Centaur rocket into the sky. They were small by cosmic standards, barely 700 kilograms each, but what they carried was priceless. Inside each craft, nestled among sensors and transmitters, was a golden record, a disc of copper plated in gold that contained greetings, sounds, and music from Earth. It was a message to anyone, or anything, that might one day find it. The golden record bore instructions on how to play it, encoded in simple diagrams, and a map showing the location of the Sun relative to 14 pulsars, celestial beacons scattered through the galaxy. Etched into the record were greetings in 55 human languages, from ancient Sumerian to modern English, as well as whale songs, thunder, laughter, and the slow heartbeat of a mother and child. To those who created it, the record was not just a token of science, but a statement of hope, that even in a universe vast beyond comprehension, life could announce itself. The first planet they visited was Jupiter, the colossal king of the solar system. When Voyager 1 arrived in early 1979, the images it sent home transformed everything we thought we knew. Jupiter was alive with storms the size of continents, its atmosphere streaked with swirling bands of cloud and color. The Great Red Spot, once thought to be static, pulsed and shifted like a living wound in the planet's surface. Lightning storms erupted deep in its clouds, and its moons revealed secrets of their own. Io, one of Jupiter's 4 great moons, astonished scientists with its erupting volcanoes, proof that worlds beyond Earth could be geologically active. Europa, smooth and pale, showed a cracked, icy surface that hinted at an ocean hidden beneath. In those first photographs, humankind saw the possibility that life might exist elsewhere in our solar system, beneath layers of ice and darkness. After Jupiter came Saturn. Voyager 1 swept past it in late 1980, revealing the planet's rings in astonishing detail. They were not solid bands of ice and dust, as once believed, but intricate systems of countless fragments, tiny icy worlds each orbiting at its own speed. Saturn's moon Titan revealed a thick orange haze, an atmosphere rich in organic compounds. Voyager 2 followed, confirming the existence of faint new moons hidden within the rings, their orbits maintained by delicate gravitational balances. Beyond Saturn, the two spacecraft parted company forever. Voyager 1, having completed its primary mission, was aimed above the plane of the solar system, toward the northern reaches of the Milky Way. Voyager 2 continued onward, toward Uranus and Neptune, on a path no other probe has ever taken. In 1986, it passed Uranus, a world turned on its side, spinning like a rolling marble. Its atmosphere glowed in muted green, with rings so dark they were barely visible. 3 years later, Voyager 2 reached Neptune, the outermost planet, and saw a place of fierce winds and deep blue storms. Its largest moon, Triton, revealed geysers of nitrogen ice erupting from its frozen surface. These encounters marked the end of their grand tour of the planets. But for the Voyagers, the journey was only beginning. Their cameras were shut down to conserve power, but their sensors still listened to magnetic fields, cosmic rays, and the faint hiss of charged particles from the sun. They were now explorers of a new frontier, the outermost boundary of the sun's influence, the region where the solar wind fades and interstellar space begins. The sun does not stop at the last planet. It breathes, and its breath fills a vast bubble known as the heliosphere. The solar wind, a constant stream of protons and electrons, flows outward in every direction, shaping a protective cocoon around the solar system. This wind travels at hundreds of kilometers per second, but eventually it meets the thin gas that fills the space between stars, the interstellar medium. When the two collide, the solar wind slows, compresses, and heats, forming a boundary called the termination shock. Voyager 2 crossed this shock in December of 2004 at a distance of roughly 14 billion kilometers from the Sun. Voyager 1 followed soon after, measuring the same transition in a slightly different region. Beyond the shock lies the heliosheath, a turbulent zone where solar and interstellar particles mingle. It is a region of compressed plasma and tangled magnetic fields, where energy and matter from the Sun meet the greater forces of the galaxy. Years later, Voyager 1 reached the final frontier, the heliopause. On August 25, 2012, it crossed into interstellar space. Its sensors recorded a sudden rise in the density of charged particles and a drop in the solar wind's flow. The magnetic field, long dominated by the Sun, aligned itself with the broader galactic field. The spacecraft had entered the space between stars. That moment was history. For the first time, an artifact of Earth had left the realm of the Sun. It was not an empty void that Voyager entered, but a turbulent, pressurized boundary where the winds of two different worlds collide. The heliopause is not static. It breathes with the rhythm of the solar cycle. As the Sun grows more active, the heliosphere expands outward. As it quiets, the bubble contracts. In this living borderland, the forces of our star meet the vastness of the galaxy, and Voyager drifts silently through their conflict. Even now, the spacecraft continues to send back data, faint signals that take over 20 hours to reach Earth. Its power, drawn from the slow decay of plutonium, wanes each year, but its voice endures. Voyager 2 crossed the heliopause in November of 2018, confirming that the solar bubble is not perfectly round, but shaped like a comet, distorted by the motion of the solar system through the interstellar medium. The two Voyagers, now separated by billions of kilometers, drift through different parts of that boundary, charting a frontier that humanity had never seen. They are the farthest human-made objects in existence. Beyond their golden records and their scientific instruments, they carry something more enduring: the idea that knowledge has no boundary and that even the smallest spark of curiosity can illuminate the deepest dark. Their journey reminds us that the edge of the Sun's influence is not the end of the story, but the beginning of our entry into the galaxy itself. Voyager 1 and Voyager 2 now travel through a region that no human could ever experience directly. The sunlight that once guided them has faded to a pale whisper, its warmth too faint to feel. The temperature around them is only a few degrees above absolute zero, and the darkness is nearly perfect, broken only by the thin glow of distant stars. Yet their instruments continue to listen, recording the faint hum of plasma waves that ripple through the interstellar medium. These vibrations, once thought impossible to detect, reveal that space itself is alive with motion. When Voyager 1 crossed the heliopause, scientists expected that the transition into interstellar space would be dramatic, a sudden plunge from the influence of the Sun into a foreign realm. But the reality was subtler, more beautiful. The spacecraft did not fall off a cliff, it drifted through a veil. the density of charged particles rose, the solar wind disappeared, and the magnetic field shifted slightly in orientation, but not abruptly. It was as though Voyager had passed through the atmosphere of one world into another, so gently that only its instruments could tell the difference. This discovery changed how we think about the sun's boundary. The heliosphere is not a bubble in the ordinary sense. It is a moving, flexible structure shaped by both the pressure of the solar wind and the forces of the galaxy around it. Imagine a comet's tail stretching behind the sun as it travels through space, the solar wind pressing outward while the interstellar medium flows around it. The sun, though it feels still to us, races through the galaxy at nearly 20 kilometers per second, dragging the entire heliosphere along with it. Voyager's measurements show that the heliopause is slightly closer to the sun on the side facing our galactic motion and stretched outward on the opposite side. Within the heliosphere, we are sheltered from much of the galaxy's high-energy radiation. Cosmic rays, charged particles traveling near the speed of light, stream through interstellar space from distant supernova and black holes. When they encounter the heliosphere, most are deflected by the sun's magnetic field. This protection is not perfect, but it is vital. Without it, Earth's atmosphere would be bombarded by a torrent of energetic particles, and life as we know it might not exist. Voyager's crossing into interstellar space revealed just how effective that shield is. Outside the heliopause, the intensity of cosmic rays increases sharply, rising by more than a factor of 4. The spacecraft also revealed something else, something unexpected. Beyond the heliopause, the density of the plasma, the soup of charged particles that fills space, was higher than anyone had predicted. Scientists had imagined that interstellar space was nearly empty, but Voyager found that it was more crowded, more dynamic. The interstellar medium pressed against the heliosphere like an ocean against a ship's hull, bending and shaping it. This pressure balance determines how far the sun's influence can reach. When the solar wind weakens, the heliosphere contracts. When it strengthens, it swells outward. Voyager 2's later crossing confirmed that the boundary is not identical in all directions. The heliopause lies closer to the sun in some regions, farther in others, a result of the uneven flow of interstellar gas and the motion of the sun itself. Together, the two spacecraft gave us our first real map of this cosmic frontier. They revealed that the sun's domain is not spherical but distorted, a shimmering bubble of plasma embedded within the galaxy's great magnetic web. For decades, scientists had debated whether the heliopause marked the true beginning of interstellar space. Voyager's data settled the question. The spacecraft detected a sudden silence in the solar wind, followed by the faint hiss of plasma oscillations from the interstellar medium. These oscillations are the signature of a new environment, where the particles are no longer bound to the sun's magnetic field. The Voyagers had indeed left the solar system, not in the planetary sense, but in the magnetic and physical sense. They had passed beyond the sun's influence and into the galactic ocean. Their journey through this frontier has also deepened our understanding of cosmic rays, magnetic reconnection, and the flow of energy between stars. By measuring the density and direction of interstellar particles, Voyager has shown that the galaxy is not a uniform space, but a complex, dynamic environment. Shock waves from distant supernova ripple through it, compressing gas and bending magnetic fields. These forces, though invisible, shape the structure of the Milky Way itself. The Voyagers now travel through this region at nearly 17 kilometers per second. At that speed, they cover almost 500 million kilometers each year, an immense distance by human standards, yet only a tiny step compared to the distances between stars. The nearest star system, Alpha Centauri, lies more than 4 light-years away. At their current velocity, the Voyagers would take 75,000 years to reach it. Even so, they remain our only emissaries to that scale of space. Each day, the faint signal from Voyager reaches Earth after more than 20 hours of travel, carrying only a few bits of information per second. The strength of that signal is unimaginably small, less than 1/10,000,000th the power of a watch battery. Yet NASA's Deep Space Network can still detect it, amplifying and decoding those whispers from the edge of the sun's domain. Within that data lie plasma densities, cosmic ray counts, and magnetic field readings that no other instrument has ever measured. The continuing success of the Voyagers is not merely a triumph of engineering, it is a testament to human foresight. The spacecraft were built in an era when computers were weak and memory scarce, yet their design was elegant and robust. Their power comes from 3 small radioisotope thermoelectric generators, each fueled by the decay of plutonium-238. As the plutonium decays, it produces heat, which is converted into electricity. Over time, the output declines, and engineers at NASA have had to turn off non-essential instruments to conserve energy. By the mid-2030s, the Voyagers will likely fall silent, but even then, they will not stop. Long after they cease to transmit, the Voyagers will continue their slow voyage through interstellar space. In about 300 centuries, Voyager 1 will pass within 2 light-years of a faint red star in the constellation Camelopardalis. Voyager 2, on its own trajectory, will drift toward the star Ross 248, arriving within a few light-years in about 40,000 years. Neither encounter will be close enough for capture, but both will carry the story of Earth into the stars. The golden records aboard them will endure for perhaps 1 billion years, their etchings preserved in metal, waiting for another intelligence to find them. And if that ever happens, those distant minds will learn that the beings who built these spacecraft once lived on a small world orbiting an average star in an ordinary spiral galaxy. They will see the drawings of our anatomy, hear our languages, and feel our music. They will know that we existed and that we wondered. Voyager's journey is a reminder that curiosity is the most powerful force in the universe. It has carried us from firelight to starlight, from the cradle of our planet to the edge of the sun's breath. The spacecraft themselves are small, but the idea behind them is infinite, that the desire to know is as natural as the stars themselves. The boundary of the sun's influence is not a limit, but a threshold, and the Voyagers are the first to cross it, leaving behind not only data and discovery, but a promise that humanity will always seek what lies beyond. As the Voyagers drift onward, their signals grow fainter with each passing year, yet they still whisper to us across the dark. Each photon of radio energy that leaves those ancient antennas travels through 1 billion kilometers of emptiness before brushing the great dishes of Earth's deep space network. When engineers first detect the signal, it is weaker than the background noise of the universe itself, so faint that it must be teased from the static like a heartbeat beneath thunder. Still, it is there, a steady pulse, a proof that something made by human hands continues to exist far beyond the reach of sunlight. Every time Voyager sends a signal home, it carries more than data. It carries continuity. In the silence between stars, it represents the persistence of curiosity, the idea that exploration does not end with the edge of the map. Inside those faint transmissions lie the vibrations of plasma waves, the counts of cosmic rays, the delicate signatures of the interstellar magnetic field. They tell us what no one had ever known before, that the space between stars is not truly empty, but alive with motion, density, and force. The interstellar medium that surrounds the Voyagers is made mostly of hydrogen, with traces of helium and dust left over from long-dead stars. Each atom out there tells a story. Some were forged in the heart of massive suns that exploded billions of years ago, scattering heavy elements across the galaxy. Others have drifted untouched since the birth of the universe, survivors from the first great expansion of space and time. These atoms now wash gently over the Voyagers, whispering their ancient tales to instruments that will one day go silent. What Voyager has found beyond the heliopause is not a void, but a balance, a frontier where the sun's breath meets the pressure of the galaxy. The magnetic field out here is stronger than expected, bending and twisting under forces too vast for comprehension. The plasma is denser, almost 3 times what models had predicted, suggesting that the Sun is moving through a region of the interstellar medium denser than average. This could be the result of a cloud of gas drifting through the Milky Way, or the remnants of an ancient shockwave from a distant supernova. Whatever its origin, it is the first tangible evidence of the cosmic weather that surrounds our solar system. By listening to the frequency of plasma vibrations, Voyager's instruments have even measured the temperature of interstellar space. It is astonishingly cold, only a few degrees above absolute zero. Yet, in this coldness, energy flows continuously. Charged particles stream through the void, guided by the galactic magnetic field like invisible currents in an endless sea. Voyager has become our first ship to sail those currents. It is easy to think of space as fixed and eternal, but Voyager reminds us that even here, everything changes. The Sun's own motion through the galaxy alters the shape of the heliosphere. Every 200 million years, the solar system completes one orbit around the Milky Way, passing through different regions of interstellar gas and dust. Some are dense and turbulent, others are thin and quiet. As we move, the size of our protective bubble swells and shrinks. The edge of the heliopause is not permanent. It breathes, responding to the rhythm of the galaxy itself. For now, both Voyagers travel through relatively calm waters. But far ahead, perhaps thousands of years from now, they may pass into regions where the density of interstellar gas rises sharply. In such a place, the heliosphere would shrink, compressing inward toward the planets. The Earth would then be exposed to more cosmic rays, altering its atmosphere in ways no one can predict. In this sense, Voyager's data is not only about exploration, but about survival. It tells us how our solar system interacts with the wider galaxy, knowledge that may one day help protect our descendants from the changing tides of space. When Voyager 1 crossed the heliopause in 2012, humanity had no eyes to see it and no ears to hear it. There was only the faint change in numbers on a screen, a rise in cosmic ray counts, a shift in magnetic direction. Yet that invisible moment was as profound as the first step on another world. It marked the crossing of a boundary that had existed since the birth of the solar system, a threshold between the domain of one star and the interstellar medium that connects them all. Voyager 2's later crossing in 2018 confirmed that the heliopause is not smooth or even. In some regions, it appears to ripple, shaped by magnetic turbulence and the flow of interstellar gas. The two spacecraft, separated by billions of kilometers, experience the crossing differently, as though the edge of the Sun's influence were alive, flexing and shifting like the surface of a living organism. These discoveries forced scientists to rethink how stars interact with their surroundings. The heliosphere, once thought of as a shield, may also be a transmitter, leaking energy and magnetic fields into the galaxy around it. Even now, the Voyager's instruments detect faint oscillations that may come from shocks traveling outward from solar eruptions years before. Those waves ripple through the heliosphere, striking the heliopause and echoing back across the void. It means that, even at 20 billion kilometers away, the heartbeat of the Sun can still be felt. The Voyagers are listening to the pulse of our star, translated into the language of plasma and magnetism. Their time is nearly over. Each year, NASA engineers must choose which instruments to power and which to shut down. The spacecraft's electrical output declines slowly, like a fading heartbeat. One by one, systems go quiet, their circuits resting after decades of service. Within a decade, perhaps less, the final transmitters will go dark. The Voyagers will then continue their journey in silence, carrying their golden records through the galaxy. And yet, the end of their transmissions will not be the end of their story. The Voyagers will orbit the Milky Way for billions of years. They will outlast the continents, the oceans, and perhaps the species that built them. Long after the Sun swells into a red giant and fades to a white dwarf, those tiny probes will still drift among the stars, silent but enduring. They are the most durable monuments humanity has ever made, not of stone or steel, but of purpose. Someday, perhaps far beyond the span of history, another civilization may find one of them. They might lift the golden record from its cradle and play the sounds etched upon it. Greetings, laughter, the rustle of wind in trees, the sound of rain falling on a lake. They might wonder what kind of beings sent these messages, and what world once circled the faint star marked on the record's map. They will know that, long ago, in a small solar system on the edge of the Milky Way, there lived a species that reached for the unknown. The Voyagers will never come home, but in a sense, they already have. Their journey is our journey, the story of a civilization that refused to let the horizon be the end. They have crossed the boundary of the sun's influence and entered the space between stars, carrying with them the evidence that curiosity is stronger than time, and that even in the silence of infinity, humanity has found a way to speak. The space beyond the heliopause is not the empty nothingness many once imagined. It is the true ocean of the galaxy, a boundless expanse filled with the faint breath of creation itself. Out here, beyond the reach of the solar wind, the sun's warmth is gone, its magnetic influence spent. What remains is the interstellar medium, a thin, ghostly fog of gas, dust, and radiation that stretches between the stars. It is so sparse that a single cubic meter of it contains fewer atoms than a single breath of air on Earth. Yet over the scale of light years, its total mass outweighs all the planets combined. It is the material from which stars are born and to which they return when they die. Voyager 1 now sails through this invisible sea. Its instruments have tasted its currents and measured its density. They have found that the interstellar medium is far denser and more turbulent than expected, filled with waves and eddies of magnetized plasma. Every few months, the spacecraft detects vibrations, slow, rhythmic oscillations of charged particles that sweep through space like ripples in a cosmic pond. These waves are not caused by the sun, but by the galaxy itself. They are the murmurs of distant supernovae, the aftershocks of stars that exploded thousands of years ago. Each pulse carries the energy of stellar death and rebirth, crossing billions of kilometers before touching Voyager's sensors. This is the true interstellar environment, the realm between suns. It is ancient and ever-changing, shaped by both destruction and creation. Within it float clouds of hydrogen and helium gas, remnants of the Big Bang, enriched by the heavier elements forged in stars. Over millions of years, these clouds collapse under their own gravity, forming dense molecular regions where new stars ignite. The interstellar medium is not static, it breathes. It is the bloodstream of the galaxy, circulating matter from one generation of stars to the next. If we could see it with our eyes, it would appear as a vast, faint glow scattered with filaments and shadows. In some regions, the gas is ionized by radiation, glowing softly in ultraviolet light. In others, it is cold and dark, so dense that even starlight cannot pass through. These are the nurseries of stars, molecular clouds like Orion, Taurus, and Perseus, where gravity gathers atoms into clusters until the pressure within them ignites fusion. The same process that created the sun is still happening all across the Milky Way, hidden within the veils of dust that drift between the stars. Yet the interstellar medium is not only a birthplace, it is also a battlefield. Shockwaves from supernovae sweep through it at thousands of kilometers per second, heating the gas to millions of degrees and scattering it across light years. As these waves expand, they collide with cooler clouds, compressing them and triggering new rounds of star formation. This cycle of destruction and renewal is what keeps galaxies alive. Every atom of carbon in our bodies was once part of this process, born in a dying star and scattered through interstellar space before finding its way into the sun and the Earth. The interstellar medium is structured like a tapestry woven from invisible threads. Magnetic fields stretch across it, shaping the flow of gas and dust into long filaments that span hundreds of light years. These magnetic lines guide charged particles, channeling the movement of cosmic rays throughout the galaxy. They are the skeleton of the Milky Way, unseen but fundamental. Voyagers' instruments, though limited, have detected hints of this structure, sensing the direction of the magnetic field and how it changes over time. What they have found suggests that the Sun and its heliosphere move through a larger magnetic domain, a region of the galaxy known as the local interstellar cloud. This cloud is vast, spanning dozens of light years, but astonishingly tenuous. It contains perhaps a tenth of an atom per cubic centimeter, yet it exerts enough pressure to shape the heliosphere and influence the cosmic environment of Earth. Our solar system has been traveling through it for the last few 100,000 years, and will eventually move beyond it into an even emptier region. When that happens, the size and shape of the heliosphere will change again. In this way, the interstellar medium is not a backdrop, but an active participant in the story of our solar system. The temperature of the interstellar medium varies across unimaginable ranges. In some regions, it is heated to millions of degrees by shockwaves from supernovae. In others, it cools to only a few degrees above absolute zero, forming dense molecular clouds where hydrogen condenses into ice and dust grains. Despite its extreme thinness, the interstellar medium contains every element known to science: carbon, oxygen, nitrogen, silicon, and iron, all drifting through space as the raw material for future worlds. When these atoms gather around a young star, they form planets, moons, and comets. In that sense, the interstellar medium is the womb of planetary systems, and by extension, of life itself. Cosmic rays traverse this medium endlessly. They are the messengers of the galaxy, charged particles accelerated to near light speed by the explosions of supernovae and the magnetic fields of black holes. These cosmic rays fill interstellar space like invisible rain, colliding with atoms and releasing radiation. On Earth, we are shielded from most of them by the heliosphere and our atmosphere. But out here, beyond the Sun's protection, they flow freely. Voyagers' detectors have recorded their steady rhythm, revealing their energy distribution and density. They are part of the background heartbeat of the universe, shaping the chemistry of clouds and influencing how stars and planets form. When we speak of interstellar space, we often imagine isolation. Yet in truth, it is a vast web of interaction. Every star's wind carves a bubble. Like our own, every supernova stirs the gas around it, and the overlapping waves of energy create a complex, interconnected system. The galaxy is not a collection of lonely stars, but a living structure held together by gravity, magnetism, and time. Voyager's passage into this realm marks the first moment humanity has touched that interconnectedness directly. For all its emptiness, the interstellar medium carries the story of the universe written in its atoms. The hydrogen within it formed when the cosmos was young, less than 1 million years after the Big Bang. The heavier elements came later, forged in stellar cores and scattered by explosions. Dust grains, no larger than smoke particles, carry carbon compounds and frozen water, seeds that may one day become the foundation of life. Every star that dies enriches this medium, and every new star born from it carries that legacy forward. In this way, the interstellar medium is both graveyard and nursery, both past and future. Voyager 1 and Voyager 2 drift through that timeless expanse now, moving slowly through the same material that will one day form new suns. Their golden records gleam faintly in the darkness, reflecting starlight that has traveled for hundreds of years. They are not merely instruments or machines. They are emissaries of memory, sailing through the birthplace of stars and the ashes of their ancestors. And as they go, they remind us of a profound truth. The space between stars is not empty. It is filled with the raw matter of existence, the quiet pulse of creation itself. The interstellar medium is the connective tissue of the cosmos, linking every atom in our bodies to the hearts of distant suns. We are not apart from it. we are made of it. The interstellar medium, though it seems eternal, is constantly reshaped by energy and motion. Every supernova sends out a storm of shockwaves that travel across light years, compressing the gas and dust they encounter. These collisions carve out immense cavities known as superbubbles, regions where the density drops almost to nothing, while the surrounding walls glow faintly in ultraviolet light. The entire Milky Way is filled with such structures, overlapping and merging like the cells of a cosmic honeycomb. The Sun itself drifts inside one of these cavities, an ancient remnant of supernova that exploded millions of years ago in a nearby cluster of stars. Scientists call it the local bubble. This local bubble is enormous, stretching hundreds of light years across, yet astonishingly thin. Within it, the gas is so rarefied that a cubic meter might contain only a few atoms. Still, it is not empty. It glows faintly in soft X-rays, the lingering heat of the explosions that created it. The Sun travels through this bubble at tens of kilometers per second, carrying the heliosphere with it, like a ship moving through gentle surf. As it sails, it passes through clouds and filaments of denser gas, remnants of old star nurseries that mark the edge of the bubble. Voyagers' measurements help map these boundaries, giving us a glimpse of the larger cosmic neighborhood in which our solar system resides. The interstellar medium within the local bubble is dynamic. The magnetic field lines threading through it twist and bend, guiding the motion of charged particles. These lines connect distant regions of space, forming a vast network that spans the galaxy. When two magnetic fields intersect, they can reconnect, releasing enormous amounts of energy. This process, known as magnetic reconnection, is thought to power many of the energetic phenomena observed in the universe, from solar flares to the outflows of distant quasars. Voyager's instruments, though small, have recorded evidence of such events even beyond the heliopause, showing that this process occurs everywhere magnetic fields interact. It is strange to think that a place so empty could also be so alive, yet this is the paradox of the interstellar medium. It is at once desolate and fertile, a realm where destruction and creation exist in the same breath. Stars die here, scattering their elements into space, and new stars form from that same material. Life itself depends on this endless cycle. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all were once atoms drifting through interstellar space before being gathered into the cloud that formed the Sun. When the Sun dies billions of years from now, those elements will return to the same cosmic sea, to be used again in some future world. The interstellar medium also carries light in forms the human eye cannot see. Invisible radiation flows through it, microwaves, X-rays, and gamma rays, each telling part of the story of the universe. The faint cosmic microwave background, the afterglow of the Big Bang, still fills all of space, its photons stretched by expansion until they are now only a few degrees above absolute zero. Voyager's sensors cannot detect that ancient light, but it passes around the spacecraft all the same, bathing it in the memory of creation. If we could ride alongside Voyager, we would see nothing familiar. There would be no color, no glow, only an infinite blackness pierced by cold points of starlight. Yet every one of those points is connected by the interstellar medium, everyone linked through the same web of gas and magnetism. The galaxy is not a collection of isolated suns, but a single, breathing organism. The interstellar medium is its blood and breath, flowing endlessly from one generation of stars to the next. The pressures and temperatures within this medium create zones of vastly different character. There are hot regions where supernovae have recently erupted, filled with X-ray emitting plasma millions of degrees in temperature. There are warm neutral regions where hydrogen atoms drift freely, and cold molecular regions where those atoms pair up to form dense clouds. Within those cold clouds, dust grains accumulate layers of ice, forming the seeds of comets and planets. When the density becomes high enough, gravity takes hold, pulling matter inward until fusion begins. In this way, every star in the sky, including the Sun, was once part of an interstellar cloud like these. Voyager's passage through this cosmic environment has taught us that space itself is not static. Even beyond the Sun's influence, waves of energy sweep through the galaxy like tides. Some of these waves come from supernovae, others from the rotation of the galaxy's spiral arms. They compress and expand the interstellar gas, shaping its structure over millions of years. These vast flows are invisible to the eye, but Voyager's instruments have sensed their rhythm, listening to the song of the galaxy itself. Every measurement from the Voyagers deepens our understanding of how the solar system interacts with the wider universe. By comparing data from the two spacecraft, scientists can determine how the heliosphere responds to changes in the interstellar medium. When the Sun emits a burst of plasma from a major solar eruption, that wave travels outward for years before reaching the heliopause. There, it collides with the interstellar plasma and sends a ripple through the surrounding gas. Voyager has recorded several of these events, revealing that even at such immense distances, the Sun's influence is still felt. Through the Voyagers, we have learned that the interstellar medium is not the dark silence we once imagined, but a dynamic, evolving system. It carries the heritage of the cosmos, the ashes of old stars, and the ingredients of new ones. It shapes the structure of galaxies and determines how long planets can sustain life. It is the space between everything, and yet it connects all things. For humans, the term interstellar once meant impossibility. It meant a gulf too wide to cross, a dream beyond reach. But now, two small spacecraft have made that crossing. They have shown us that the boundary between stars is not infinite but continuous, that the space beyond the Sun's light is a place we can know, measure, and one day perhaps traverse. As Voyager drifts onward, its power fading and its sensors dimming, it continues to send back its final whispers. Those signals remind us that we are part of a story larger than any world, a story written in hydrogen and starlight. The interstellar medium is not foreign ground, it is our origin. It is the dust of which we are made, and the destination to which all things return. And so, as the Voyagers continue into that endless expanse, they carry with them the knowledge that what lies beyond the solar system is not emptiness, but connection. It is the fabric from which stars, planets, and life itself are woven. It is the breath of the universe. In the space between the stars, distance and time lose their familiar meaning. A light year becomes not just a measure of length, but of history itself, the span between what is and what was. Every photon that travels through the interstellar medium carries with it the memory of its source, a message that may take millennia to reach another world. If one could drift in that space and listen, one would hear nothing that the ear could detect, yet the silence would not be empty. It would hum with invisible energy, the faint murmur of cosmic rays and plasma waves flowing endlessly through the galaxy. The interstellar medium is an orchestra of forces that play across scales beyond comprehension. The smallest grains of dust, charged by ultraviolet light, spin and align themselves with magnetic fields that extend for hundreds of light years. These grains emit a faint glow known as starlight polarization, the signature by which astronomers map the unseen magnetic skeleton of the galaxy. The gas that drifts between those grains forms long, sinuous structures, filaments shaped by turbulence and gravity. In some regions, the gas collapses inward, forming the dense knots that will become stars. In others, it disperses, thinned by the shockwaves of nearby explosions. Within this grand symphony, our solar system is but one moving note. As the Sun travels through the Milky Way, it passes through different regions of the interstellar medium, each with its own temperature, pressure, and magnetic structure. The heliosphere responds to these changes, expanding and contracting like a living organism. In the distant past, when the Sun may have entered a denser cloud of gas, the heliosphere would have shrunk, exposing the planets to greater fluxes of cosmic radiation. Some scientists have suggested that such passages might even influence the climate of Earth, subtly altering the rate of cloud formation or affecting the evolution of life itself. In this way, the interstellar medium is not merely a distant abstraction, it is a force that shapes the destiny of every world within the Sun's reach. The gas of the interstellar medium is mostly hydrogen, the simplest and most abundant element in the universe. It exists in several forms. There is neutral hydrogen, detectable by the faint radio emission it produces at a wavelength of 21 centimeters. There is ionized hydrogen, heated by starlight to thousands of degrees. And there is molecular hydrogen, locked in cold, dark clouds, where it binds into pairs and gathers into filaments. Around these molecules cling grains of dust composed of silicates, carbon, and frozen water. These microscopic particles are the building blocks of comets and planets. When new stars form, the radiation they emit drives shockwaves into their surroundings, dispersing this material and enriching the interstellar medium once more. Thus, every star's birth sows the seeds of the next generation. Voyagers' instruments have detected some of this structure indirectly, through the behavior of plasma and the strength of magnetic fields. The spacecraft records the density of charged particles and listens for the faint tone of plasma, oscillations. These measurements allow scientists to calculate how the interstellar medium changes over time. In recent years, they have found that the plasma density around Voyager 1 has been increasing slowly, suggesting that the spacecraft may be approaching a boundary between different regions of the interstellar cloud. Such transitions remind us that even at scales of trillions of kilometers, space is not uniform. It has weather, motion, and geography. Cosmic rays, those restless travelers from distant supernovae, move through this medium like rain carried by a wind. They are not mere curiosities, but essential elements of the galactic ecosystem. When they collide with atoms in the interstellar gas, they trigger chemical reactions that form complex molecules. These reactions create organic compounds, hydrocarbons, alcohols, even simple amino acids, that cling to dust grains and drift through space. When those grains eventually fall into a forming solar system, they become part of the chemistry of new worlds. On Earth, it may have been just such compounds that gave rise to the first living cells. In this way, the interstellar medium is not only the birthplace of stars, but also the quiet forge of life's ingredients. Beyond the reach of the Voyagers, farther still, lie denser molecular clouds, where gravity tightens its grip. In those places, temperatures fall to only a few degrees above absolute zero, and light from the galaxy's stars cannot penetrate. Within such darkness, matter gathers silently. Over time, these cold cores collapse, heating from within until nuclear fusion ignites. A new star is born, and the surrounding gas becomes a disk of dust and ice. Within that disk, small particles collide, stick, and grow, forming the first seeds of planets. The cycle continues endlessly. The interstellar medium gives birth to stars. The stars enrich the medium when they die, and the process begins again. When we look at the night sky from Earth, we are seeing only the brightest points of this vast system. The true complexity lies hidden in wavelengths invisible to the eye: infrared, radio, X-ray, where astronomers can trace the motion of gas and the temperature of dust. These observations reveal that the Milky Way's spiral arms are not static structures, but waves of density moving through the interstellar medium, compressing gas into stars and leaving behind emptier regions. Our Sun, and every planet around it, was once part of one such wave. Even now, as Voyager sails through interstellar space, it follows the motion of that wave, orbiting the center of the galaxy like a leaf caught in a slow, eternal current. The interstellar medium also carries echoes of ancient events. Gamma ray bursts, the most powerful explosions in the universe, send waves of energy that travel for billions of years. When they pass through the galaxy, they alter the chemistry of the gas they encounter, stripping electrons from atoms and creating trails of ionization. Supernova remnants, expanding like ghostly rings, enrich the surrounding space with iron, oxygen, and silicon. Over cosmic time, these processes ensure that the galaxy becomes richer and more complex. Every new generation of stars begins with material that has been shaped by those before it. Through the Voyagers, we are now directly sampling this eternal cycle. The instruments aboard them measure not just plasma density and magnetic direction, but the very conditions that define our galactic environment. For the first time, humanity has touched the interstellar medium, felt its rhythm, and measured its strength. We now know that the Sun and its planets drift within a living network of energy and matter, a system far larger than any world, yet intimately connected to all of them. Out here, where the solar wind has faded and the light of the Sun is weaker than the stars around it, the Voyagers drift in silence. Yet they are not lost. They are part of the great flow that binds every star in the Milky Way together. Each second they move farther into the interstellar medium, and with every kilometer, they carry with them the story of a species that once looked up and asked what lies beyond. The interstellar medium has no boundary. It stretches in every direction, merging eventually with the space between galaxies themselves. It is the connective tissue of the universe, the thread that links creation to destruction and life to death. In its vast quiet, the Voyagers drift like thoughts in the mind of the cosmos, and as they do, they remind us that space is not emptiness, but potential, the endless field from which everything arises and to which everything will one day return. Far beyond the orbits of the planets, past the heliopause where the solar wind yields to the interstellar breeze, lies a frontier even more mysterious. A vast, invisible halo of ice and ancient debris that surrounds the solar system like a ghostly shell. This is the Oort cloud, a realm so distant that sunlight takes months to reach its outer edge, and so faint that no telescope has ever seen it directly. Yet its existence is certain, written in the long, slow arcs of comets that occasionally fall toward the Sun from the farthest reaches of space. The Oort cloud marks the final whisper of the Sun's influence. It is the outermost remnant of the solar system's birth, a spherical cloud of icy bodies extending nearly halfway to the nearest stars. The inner edge begins tens of billions of kilometers from the Sun, far beyond the orbits of Neptune and Pluto, while the outer edge may reach as far as 2 trillion kilometers away, so distant that the Sun would appear only as a bright star among others. Within this immense sphere, trillions of frozen fragments drift silently, each a relic from the dawn of the solar system. To understand how the Oort cloud formed, we must return to the beginning. Over 4.5 billion years ago, the Sun was born from a collapsing cloud of gas and dust. As the new star ignited, the remaining material flattened into a disk where planets took shape. The inner regions, scorched by heat, formed rocky worlds. The outer regions, cold and vast, gave rise to giants of gas and ice. But not all of the material in that disk found a stable orbit. Some was flung outward by the gravitational pull of Jupiter and Saturn, ejected from the young solar system at great speed. Most of that debris escaped into interstellar space, never to return. But a small fraction did not travel far enough to break free. Instead, the gravity of nearby stars and the tidal forces of the galaxy itself slowed and scattered those icy remnants, capturing them into distant elliptical orbits around the Sun. Over millions of years, their paths randomized, forming a vast spherical cloud that now surrounds the solar system in every direction. This, astronomers believe, is the Oort cloud, named after the Dutch astronomer Jan Oort, who first proposed its existence in the 1950s to explain the origin of long-period comets. Long-period comets are among the most beautiful and enigmatic visitors to the inner solar system. Their orbits are immense, taking them from the outermost reaches of the Oort cloud to within a few million kilometers of the Sun. When they approach the inner system, the heat of sunlight vaporizes their icy surfaces, forming glowing tails that stretch across the sky. After their brief display, they retreat once more into the dark, perhaps never to return. The fact that such comets appear from every direction, rather than from a single plane, is one of the strongest pieces of evidence for the Oort cloud's spherical nature. The scale of this region defies imagination. If the solar system were reduced to the size of a coin, the Oort cloud would extend several meters in every direction. Within that vast sphere, the density of objects is incredibly low, perhaps only a few per cubic light-year. Yet because the Oort cloud encompasses such a huge volume, it may contain more material than all the planets combined. Each of its icy bodies, from pebble-sized grains to mountains of frozen water and rock, is a pristine time capsule from the solar system's infancy. Occasionally, the delicate balance of these distant orbits is disturbed. A passing star, or even the slow tidal pull of the Milky Way, can nudge an Oort cloud object from its stable path. Once disturbed, the object begins a long descent toward the inner solar system, a journey that can take millions of years. When it finally nears the Sun, it becomes visible as a comet, its tail streaming across the night sky. Some of these visitors burn away completely. Others break apart under tidal forces. A few collide with planets, leaving craters that record their fiery ends. The Oort cloud is not only the outermost boundary of the solar system, it is also a borderland between the Sun's gravity and that of the galaxy. Beyond its outer edge, the gravitational pull of the Sun fades until it is no stronger than the tug of nearby stars. There, in that fragile balance, the influence of other suns begins to dominate. It is in this distant frontier that the boundaries between star systems blur, their outer shells of comets and debris mingling like the edges of overlapping oceans. Some astronomers believe that interstellar comets, objects that wander between star systems, may have originated from these shared boundary zones. In recent years, a few such visitors have been detected passing through our solar system. First Oumuamua in 2017, then Borisov in 2019. Their trajectories showed that they came from beyond the Sun's gravitational reach, wanderers ejected from the Oort clouds of other stars. Their presence confirmed that our solar system is not isolated, but part of a galactic traffic of icy bodies moving between worlds. The outer Oort cloud is so distant that it lies far beyond the heliosphere, in true interstellar space. The inner Oort cloud, sometimes called the Hills cloud, may begin closer in, just beyond the orbit of Pluto. It forms a transition region between the scattered disk of icy objects near Neptune and the great halo beyond. The exact structure remains uncertain, but computer models suggest that the Oort cloud is shaped both by the history of the solar system and by the gravitational tides of the Milky Way itself. Over billions of years, the slow movement of the galaxy's spiral arms and the occasional passage of nearby stars have sculpted this vast sphere, giving it a subtle asymmetry. It is likely that every star has its own version of the Oort cloud, a faint shell of debris left over from its birth. Together, these overlapping halos form a kind of galactic ecosystem, an invisible network of icy reservoirs that occasionally exchange material. When two stars pass near each other, they can trade comets, seeding one another's systems with new fragments of frozen dust. In this way, the building blocks of life may travel from one star to another, carried by comets across light years of space. The Oort cloud is not just a relic of the past, it may be a bridge between worlds. No spacecraft has ever reached the Oort cloud, and none built today could make the journey within a human lifetime. Even Voyager 1, the most distant object ever created by humanity, will need tens of thousands of years to reach its inner edge. Yet through observation and simulation, we can glimpse its nature. We can see its echoes in the long tails of comets, in the periodic showers of meteorites that strike Earth, and in the subtle gravitational influence it exerts on the orbits of distant trans-Neptunian objects. If we could travel outward far enough, we would eventually reach a place where the Sun is just one star among many, its light no brighter than the other points scattered across the galactic sky. That is the edge of the Oort cloud, the true frontier of the solar system. Beyond it, the pull of the Sun weakens to nothing, and the gravitational fields of neighboring stars begin to dominate. It is there that our system ends and interstellar space begins in the fullest sense. The Oort cloud reminds us that the boundaries of the solar system are not sharp lines, but fading gradients, where the influence of one realm merges into another. It shows us that even at the farthest reaches of the Sun's domain, the story of creation continues. The icy bodies drifting through that dark sphere are not merely leftovers from the past. They are the seeds of the future, waiting to be drawn inward once more, to shine briefly as comets before returning to the cold. And beyond them lies the next chapter of the cosmic journey. For beyond the Oort cloud, the Sun's light vanishes entirely, and other suns begin to dominate the sky. There, among the endless stars of our galactic neighborhood, begins the next frontier of exploration, where the home of one star gives way to the vast company of the Milky Way. Beyond the faintest edge of the Sun's gravitational grasp, the sky begins to belong to other suns. The darkness that surrounds the solar system is not empty. It is filled with light from distant stars, each one a beacon across the gulf of interstellar space. Among them lies our nearest neighbor, a system of 3 suns bound together by gravity and by the same cosmic history that shaped our own. This is Alpha Centauri, the closest star system to the Sun, and the first step outward into the galactic wilderness. Alpha Centauri lies a little over 4 light-years away, a distance so immense that even Voyager 1, humanity's most distant probe, would need more than 70,000 years to reach it. Yet in cosmic terms, this is next door. The system is composed of 3 stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. The first 2 are bright yellow and orange suns orbiting one another every 80 years, while Proxima, a small red dwarf, circles them at a much greater distance. From the outer planets of our own system, they are invisible to the naked eye, but through a telescope, they form one of the most beautiful double stars in the southern sky. Alpha Centauri A is slightly larger and hotter than the Sun, while Alpha Centauri B is a bit smaller and cooler. Together, they create a dynamic gravitational ballet, their mutual orbit shaping a region of stability where planets could form. Around the faint companion, Proxima Centauri, astronomers have discovered at least 2 worlds. One of them, Proxima B, is about the size of Earth and orbits within the star's habitable zone, the region where liquid water could exist on its surface. The discovery of Proxima B was a revelation. It meant that the nearest star to the Sun hosts a potentially habitable planet. But life around a red dwarf would not be easy. Proxima Centauri is small, dim, and volatile, emitting powerful flares that can strip away planetary atmospheres. The light that reaches any world there would be red and subdued, and the days could last weeks or months, depending on the planet's rotation. Yet even under those harsh conditions, the possibility of life cannot be dismissed. Life, after all, has thrived in the most extreme environments on Earth, deep beneath oceans, within volcanic vents, and even inside rocks. If it can survive here, perhaps it can survive there. The Alpha Centauri system is only the most familiar of our nearby neighbors. Scattered around it are dozens of other stars within just a few dozen light years. Many of them are red dwarfs, faint and long-lived, invisible without telescopes but vastly more common than suns like ours. The nearest brown dwarfs, Lumen 16 and WISE 0855-0714, are even colder and dimmer, halfway between stars and planets. Lumen 16 glows faintly in the infrared, a pair of failed suns still radiating the leftover heat of their formation. WISE 0855-0714 is colder still, perhaps only as warm as the human body. To an observer nearby, it would look like a dim ember floating in the night. Brown dwarfs like these are reminders that not every object born from collapsing gas becomes a true star. Some fail to ignite the fusion of hydrogen and instead smolder quietly for billions of years. Yet they are part of the same family, drifting through the galaxy as silent companions to brighter suns. Around them, too, may orbit planets, cold, dark worlds bathed in the faint glow of infrared light. The galaxy is filled with such systems, unseen and uncounted. For every star like the Sun, there may be dozens of dimmer cousins wandering through the dark. The stars nearest to the Sun form what astronomers call the local bubble, a region of relatively low gas density within the Milky Way's spiral arm. Within a radius of 50 light-years, there are more than 100 stars, most smaller and cooler than ours. Some are solitary, others part of binary or triple systems. A few, like Barnard's star, are ancient red dwarfs that have been burning quietly for nearly as long as the galaxy itself. Barnard's star moves rapidly across the sky, approaching our system at a speed of over 100 kilometers per second. In only 10,000 years, it will become one of the closest stars to the Sun. Nearby, we find Wolf 359, a faint red dwarf less than 8 light-years away, and Lalande 21185, another small star that hosts at least one planet. Further still are systems like Epsilon Eridani and Tau Ceti, both sun-like stars with dusty debris disks that may mark the beginnings of planetary systems. Each of these neighbors is a potential harbor for life, though most are too distant for us to know their secrets. The instruments we have today can detect the pull of planets, and sometimes glimpse their shadows as they pass before their stars. But to see their surfaces, to know their colors and atmospheres, remains a dream for the future. Even so, we are beginning to understand that the galaxy around us is alive with planets. In the past few decades, astronomers have discovered thousands of exoplanets orbiting distant stars, using methods that measure the tiniest dips in starlight or the faintest shifts in spectral lines. These discoveries have revealed worlds larger than Jupiter, smaller than Earth, and stranger than imagination. There are planets that orbit 2 suns, worlds made of diamond, and giants so close to their stars that their atmospheres boil away into space. If such diversity exists throughout the Milky Way, then it is almost certain that somewhere among the billions of stars, there are worlds much like our own. The vast distances between stars make travel seem impossible, yet they are small on the scale of the galaxy. The Milky Way contains hundreds of billions of suns spread across a disk 100,000 light-years wide. From our vantage point, near the inner edge of one of its spiral arms, the stars appear as a scattered spray of light, but in truth, they form a continuous structure, a rotating island of energy and matter bound together by gravity and dark matter. Every point of light in the night sky is part of that immense system, each one a neighbor in the same cosmic city. In the centuries to come, the nearest stars will be our first destinations. Already, theoretical spacecraft designs, using light sails, fusion drives, or even beams of antimatter, seek to bridge the gap. A mission like Breakthrough Starshot imagines sending gram-sized probes propelled by powerful lasers, accelerating them to a fraction of the speed of light. At such speeds, a probe could reach Alpha Centauri in just a few decades. For the first time, the idea of interstellar exploration has moved from myth to mathematics. When we think of our galactic neighborhood, we must imagine more than dots of light. Each of those stars is a sun with its own planets, moons, comets, and asteroids. Some may have oceans, some may have clouds of methane or rings of ice. Others may be barren rocks scorched by radiation. But all of them are connected through the same interstellar medium that binds the galaxy together. Gravity, radiation, and time weave their fates into one immense pattern, a web of motion and energy that spans the Milky Way. Our nearest neighbors are not merely distant lights. They are part of the same story that began in the Oort cloud and stretches outward toward infinity. The dust that forms new planets in those systems is the same dust that once circled our own sun. The elements that burn in those stars are the same that course through our veins. We and they are kin, bound by physics and by the shared history of the universe. The edge of the solar system is not an end, but a beginning, a crossing into the broader company of stars. As we gaze outward from our tiny sphere of warmth, we see the Milky Way not as a foreign place, but as our true home. The stars around us are not distant, they are neighbors, each one a possible mirror of what we are and what we may yet become. Our solar system is a small island within a vast ocean of stars, a single ember adrift in the great spiral of the Milky Way. Beyond the cluster of nearby suns that make up our stellar neighborhood lies the full immensity of our galaxy, a structure so enormous that it defies human intuition. The Milky Way stretches across 100,000 light-years, a rotating disk of hundreds of billions of stars bound together by gravity, dust, and something unseen yet powerful, dark matter. From within, we see it as a faint milky band across the night sky, but from afar, it would appear as a magnificent spiral, its arms coiling gracefully around a bright central core. Our place within this galaxy is modest. The Sun orbits near the inner edge of a minor spiral spur known as the Orion Arm, a branch that lies between two larger arms, the Sagittarius Arm toward the Galactic center and the Perseus Arm farther outward. The Orion Arm is not a grand structure, but it is home to familiar landmarks: the bright Orion Nebula, the Pleiades Cluster, the Horsehead Nebula, and thousands of stars that have shaped our myths and calendars since before recorded history. Our solar system, circling the galactic center at more than 200 kilometers per second, completes one full orbit every 200 million years. Since the birth of the dinosaurs, the Sun has made only 1.5 such revolutions. From this perspective, humanity is new to the galaxy, a young species in an ancient domain. Yet our curiosity has already carried us beyond the planets, beyond the heliosphere, into the wider galactic stage. The Milky Way is both our home and our frontier. To understand it is to understand the structure of everything that exists within the visible universe. The galaxy's disk is its most recognizable feature. It is a flat, rotating plane about 1,000 light-years thick, filled with stars, nebulae, and swirling clouds of gas and dust. Within this disk, new stars are born every day in vast molecular clouds. These clouds collapse under gravity, forming bright clusters that illuminate the surrounding regions. Between the glowing arms lie darker voids, lanes of dust that absorb starlight and mark the paths of interstellar matter. This interplay of light and shadow gives the Milky Way its mottled texture, a tapestry of brightness and obscurity that tells the story of ongoing creation. At the center of the galaxy lies a dense, luminous bulge containing older stars and clusters orbiting a hidden mass, a supermassive black hole known as Sagittarius A star. This object, with a mass of 4 million suns, anchors the entire Milky Way. Around it, stars whip through space at thousands of kilometers per second, their orbits revealing the invisible gravity that binds them. In 2022, astronomers captured the first image of this black hole's shadow using a global network of telescopes. It appeared as a glowing ring surrounding a dark core, the silhouette of a region where gravity is so intense that not even light can escape. Surrounding the galactic disk is a vast, spherical halo made of ancient stars, globular clusters, and an invisible component we can only infer: dark matter. This halo extends far beyond the visible boundaries of the galaxy, reaching distances of hundreds of thousands of light years. The stars within it are relics from the Milky Way's earliest days, older than the Sun by billions of years. They orbit in elongated paths that cut through the disk, tracing the remnants of smaller galaxies that were long ago absorbed by our own. The halo is the Milky Way's memory, a record of its violent and beautiful history. Dark matter is the invisible scaffolding that holds the galaxy together. Though we cannot see it, its gravity shapes the motion of every star and planet. Without it, the Milky Way's outer regions would fly apart, their stars moving too fast to remain bound. Astronomers estimate that dark matter outweighs ordinary matter by a factor of 5. It is everywhere, yet it interacts with nothing but gravity. What it is remains one of the greatest mysteries of modern physics. Some theories suggest it is composed of exotic particles that rarely collide with ordinary matter. Others propose that it is a manifestation of deeper geometric properties of space-time. Whatever the answer, it defines the architecture of the cosmos. The Milky Way itself is not static. It breathes, rotates, and evolves. Stars are born in its arms, live for millions or billions of years, and die in spectacular explosions that seed the surrounding space with heavy elements. Supernovae sculpt the interstellar medium, driving waves of gas that ripple through the disk. These waves trigger new rounds of star formation, creating a continuous cycle of birth and destruction. The galaxy is a living system, its heartbeat measured in millions of years. Our galaxy is also not alone. It is part of a small collection of about 80 galaxies known as the Local Group. The two largest members are the Milky Way and the Andromeda Galaxy, a spiral much like our own. The Andromeda Galaxy lies about 2.5 million light-years away, and it is moving toward us. In roughly 4 billion years, the two galaxies will collide, merging into a single, larger, elliptical galaxy. For the stars within them, this collision will not be an apocalypse, but a ballet. The distance between stars is so vast that few will ever collide directly. Instead, they will drift through one another, their orbits reshaped by gravity. Over time, the Milky Way and Andromeda will blend, their gas clouds forming new generations of stars amid the ruins of the old. Beyond the Local Group lies the Virgo supercluster, an enormous aggregation of thousands of galaxies bound by gravity. Yet even that is only a small part of a still larger structure known as the Laniakea supercluster. This colossal formation, spanning more than 500 million light-years, contains our Local Group along with many others. It is one of the great filaments of the cosmic web, a network of clusters and voids that defines the large-scale structure of the universe. Gravity pulls galaxies along these filaments, while the mysterious force known as dark energy drives the overall expansion of space itself. Within this grand design, our place is minute, yet it is real. The Orion Arm, the Milky Way, the Local Group, all are steps in a hierarchy that stretches from the scale of planets to the scale of the cosmos. The same physical laws that govern the orbit of Earth around the Sun govern the orbit of the Milky Way within Laniakea. The same forces that shape the path of a comet shape the motion of entire galaxies. It is a continuum of structure, a harmony of motion that unites everything from atoms to clusters of galaxies. When we look up at the Milky Way on a clear night, we are seeing across thousands of light-years of space. Each star is part of a spiral arm, moving in concert with billions of others. The light that reaches our eyes began its journey long before humanity existed. To gaze at the galaxy is to look backward in time, to witness the sum of all creation. The wilderness beyond the solar system is not chaos but order, the vast, elegant order of gravity, magnetism, and time. The Milky Way is both cradle and cosmos. It shelters us, feeds the birth of new worlds, and will one day reclaim us when our sun dies. Yet beyond even this colossal home lies something greater still. The galaxy is only one of hundreds of billions, each with its own stars, planets, and histories. Between them stretches the intergalactic void, an even deeper ocean where the structure of the universe itself begins to take form. It is toward that infinite gulf that our imagination must now travel. For beyond the galactic wilderness lies the true architecture of existence, the web that binds all galaxies together across the cosmic dark. Beyond the luminous spiral of the Milky Way lies an ocean of unimaginable emptiness, a gulf so vast that even the nearest galaxies appear as faint smudges of light. This is the intergalactic void, the great dark between the islands of stars. It is the space where gravity loosens its hold, where matter becomes rare, and where the universe's deepest structure begins to reveal itself. The distances here are so immense that they can scarcely be grasped. The nearest galaxy beyond our own, Andromeda, lies 2.5 million light-years away. Even light, traveling at nearly 300,000 kilometers per second, requires more than 2 million years to cross the gulf between us. The void between galaxies is not completely empty. It is filled with the intergalactic medium, a thin, nearly invisible gas of hydrogen, helium, and plasma that stretches across the cosmos. In some regions, it is so tenuous that a cubic meter of space contains fewer atoms than the best vacuum created on Earth. Yet over the scale of billions of light-years, this diffuse matter adds up to more mass than all the stars and planets combined. It forms the filaments of a colossal structure known as the cosmic web, the hidden skeleton of the universe. The cosmic web is one of the most breathtaking discoveries in modern astronomy. Through the observation of distant galaxies and the faint glow of ancient hydrogen gas, scientists have mapped its shape, a vast, interconnected network of filaments and nodes that stretch across the cosmos. At the intersections of these filaments lie clusters of galaxies, bound together by gravity. Between them lie immense voids, each tens or even hundreds of millions of light-years across, where matter is scarce and light is faint. From a cosmic distance, the universe resembles a web of luminous threads woven through darkness, a structure both delicate and immense. Our galaxy, the Milky Way, is one of many caught in this web. Together with the Andromeda Galaxy and about 80 smaller companions, it forms the Local Group, a gravitationally bound family of galaxies roughly 10 million light-years wide. Most of the members are small and faint dwarf galaxies, their stars numbering in the millions rather than billions. They orbit the larger galaxies like moons around planets, some slowly merging, others being torn apart by tidal forces. The Magellanic Clouds, visible from the southern hemisphere, are two of these dwarf companions. They are satellites of the Milky Way, spiraling around it in elongated orbits and leaving behind trails of gas that glow faintly in ultraviolet light. Within the Local Group, the Milky Way and Andromeda dominate. The two galaxies are drawn toward each other by their mutual gravity, destined to collide in about 4 billion years. Around them, smaller galaxies orbit like sparks around a fire. The entire group, in turn, moves as a single entity through space, falling toward a much larger structure, the Virgo cluster. This cluster, located about 50 million light-years away, contains more than 2,000 galaxies bound together in a massive gravitational knot. Many of its members are elliptical galaxies, ancient and quiescent, their star formation long-ended. The Virgo cluster is the heart of a still greater formation, the Virgo supercluster. For decades, astronomers believed that the Virgo supercluster defined our cosmic address, but modern mapping has revealed a grander truth. The Virgo supercluster is only one part of an even larger structure called the Laniakea supercluster. Spanning over 500 million light-years, Laniakea contains more than 100,000 galaxies, including our Local Group, the Virgo cluster, and many others. Its name, derived from Hawaiian, means immense heaven. It is an appropriate title, for Laniakea represents one of the largest known coherent structures in the observable universe. Within it, rivers of galaxies flow along gravitational currents toward a common center known as the Great Attractor, a region of deep gravitational pull, located about 250 million light-years away. These vast motions of galaxies form the grand choreography of the cosmos. Though the universe is expanding, gravity continues to draw galaxies together into clusters and superclusters, even as the overall fabric of space stretches. Within the cosmic web, matter is not evenly distributed. Instead, it is concentrated along filaments where galaxies form like dewdrops on cosmic threads. The voids between these filaments are nearly empty, containing only the faintest traces of hydrogen and the occasional lonely galaxy drifting through the dark. These voids are not dead, however. They expand faster than the regions of greater density, pushing the web outward and giving the universe its evolving shape. The intergalactic medium itself is a relic of the early universe. After the Big Bang, matter was distributed almost uniformly, but over billions of years, gravity gathered it into denser regions, while dark energy drove the expansion of space. Today, the intergalactic medium remains as a faint echo of that primordial state. It glows weakly in X-rays and ultraviolet light, heated by the radiation of galaxies and quasars. This glow, though invisible to the human eye, forms a diffuse background that astronomers can detect through sensitive instruments. It is the whisper of the universe itself, a record of its growth and transformation. Dark matter and dark energy dominate this cosmic landscape. Dark matter, though invisible, provides the gravitational scaffolding on which galaxies form, while dark energy drives the expansion of the universe at an accelerating pace. The interplay between these two unseen forces defines the fate of all things. Gravity pulls matter together, forming galaxies and clusters. Dark energy pushes them apart, expanding the space between them faster with each passing billion years. In the distant future, the accelerating expansion may tear the cosmic web apart, isolating each galaxy in an ever-growing void. Between galaxies, time feels different. The emptiness stretches perception, and the scale becomes overwhelming. If one could stand in the intergalactic void and look around, one would see only faint smudges of light scattered across a black horizon. The nearest galaxy might be millions of light-years away, glowing faintly in blue and gold, while the rest would appear as tiny sparks, their light crossing unimaginable distances. The silence would be absolute, yet filled with the echo of expansion, the slow stretching of space itself. The intergalactic void is both a frontier and a mystery. It represents the largest scale of structure we can observe, and beyond it lies the unknown. What happens beyond the boundaries of the cosmic web? Does the pattern continue indefinitely, or does it dissolve into something beyond our comprehension? Every observation hints that the web extends as far as we can see, limited only by the age of the universe and the speed of light. Beyond that limit lies the unobservable universe, regions forever hidden from us, separated not by space, but by time itself. Our journey outward, from the planets to the heliopause, from the Oort cloud to the nearest stars, and now to the intergalactic void, reveals a universe both connected and infinite. Every level of structure, solar system, galaxy, cluster, supercluster, follows the same laws, born from the same explosion that began it all. Yet each step outward brings us closer to the ultimate question. What lies beyond everything we can see? In the next frontier, we will reach the edge of the observable universe itself, the limit imposed not by distance, but by time. It is the horizon beyond which light has not yet arrived, where the first moments of creation still glow as faint radiation. To understand what lies there is to confront the true boundary of existence, the point where space and time themselves had their beginning. The universe we can see is not infinite, though it feels that way when we look into the night sky. Every star, every galaxy, and every filament of the cosmic web lies within a vast but limited sphere, the observable universe. It is not limited by walls or edges, but by time itself. Light takes time to travel, and the farther we look, the further back in history we see. Beyond a certain distance, light has not had enough time to reach us since the birth of the cosmos. That distance, that limit, defines the edge of what we can observe, a horizon drawn not in space, but in time. The diameter of the observable universe is about 93 billion light-years. This does not mean the universe is only that large. It is simply the portion from which light has had time to arrive. The rest lies beyond our reach, expanding faster than light can cross the void. To understand why, we must remember that space itself expands. The galaxies are not flying through space as projectiles. The space between them is stretching, carrying them away from one another. This expansion, discovered in the early 20th century by Edwin Hubble, was one of the most profound revelations in science. It meant that the universe is not static, but evolving, born from a single moment of immense density and energy, the Big Bang. Looking deeper into space is like looking backward in time. The light from nearby stars left only years ago. The light from the Andromeda Galaxy began its journey 2 million years ago, before humans existed. The light from the most distant galaxies we can see left when the universe was young, only a few 100 million years old. Beyond them lies a wall of ancient radiation, the cosmic microwave background, or CMB, the afterglow of the Big Bang itself. This faint microwave signal, discovered accidentally in 1965 by Arno Penzias and Robert Wilson, fills the entire sky uniformly. It is the oldest light we can ever see, the fossilized echo of creation. When the universe began nearly 13.8 billion years ago, it was a hot, dense plasma of particles and light. At that time, photons could not travel freely. They were constantly scattered by electrons in a seething fog of energy. As the universe expanded, it cooled. After about 380,000 years, it reached a temperature low enough for electrons and protons to combine into neutral hydrogen atoms. The fog lifted, and light could finally travel unimpeded. That light still travels today, stretched by cosmic expansion into the microwave wavelengths we detect as the CMB. Every photon of that ancient radiation carries a memory of the universe as it once was, a glowing sphere of plasma, uniform to 1 part in 100,000. Yet the CMB is not perfectly smooth. Tiny variations in its temperature reveal the seeds of structure, the minute fluctuations in density that gravity would later amplify into galaxies and clusters. These ripples are the fingerprints of quantum fluctuations that occurred in the first fraction of a second after the Big Bang, when the universe underwent a period of rapid expansion known as cosmic inflation. During inflation, space itself expanded faster than the speed of light, stretching microscopic variations to cosmic scales. These fluctuations became the blueprint for the universe's large-scale structure, determining where matter would accumulate and where voids would form. The edge of the observable universe is therefore not a wall, but a horizon. Beyond it, space continues, but its light has not yet reached us. As the universe ages, this horizon grows. More distant regions become visible. However, the acceleration of cosmic expansion means that some parts of the universe are receding faster than light due to the stretching of space. Their light will never reach us, no matter how long we wait. Those regions are forever beyond observation, sealed off by the expansion itself. The expansion is driven by a mysterious force called dark energy. First discovered in the late 1990s through observations of distant supernovae, dark energy makes up roughly 70% of the universe's total energy density. Its effect is subtle yet overwhelming. It causes the expansion of the universe to accelerate over time. The more space expands, the more dark energy there seems to be, creating a feedback loop that drives galaxies farther and farther apart. In the distant future, galaxies beyond our local group will fade from view entirely, their light redshifted beyond detectability. Billions of years from now, an observer in the Milky Way's merged descendant galaxy may see only a handful of neighboring stars, unaware that a vast universe once surrounded them. The observable universe today contains more than 2 trillion galaxies, each with billions of stars. Yet everything we can see, every atom, every beam of light, every world, is only a small fraction of the total. Ordinary matter makes up less than 5% of the universe. The rest is invisible: dark matter, which binds galaxies together, and dark energy, which tears them apart. The light we see is only the surface of a much deeper reality, like the faint ripples on the ocean of existence. If we could travel to the very edge of the observable universe, we would not find an end or a barrier. Instead, we would see the same galaxies and radiation we see from here, because every point in the universe is its own center of observation. The universe has no edge in space, only in time. The horizon we perceive is like the horizon on Earth. It recedes as we move toward it. Wherever we stand, the cosmos extends equally in every direction, each observer surrounded by the same sphere of visible reality. At the largest scales, the universe appears remarkably uniform. Its geometry is flat, meaning that parallel lines remain parallel even over billions of light years. This flatness implies that the total density of matter and energy in the cosmos is finely balanced, neither enough to make space curve back on itself, nor too little to make it open endlessly. This delicate balance is one of the greatest puzzles in cosmology. It suggests that the conditions of the early universe were tuned with extraordinary precision, or that our observable patch is only one small part of a much larger and more varied whole. The light from the edge of the observable universe has traveled for nearly 14 billion years. Yet because space has expanded during that time, the regions from which it came are now more than 40 billion light years away. The universe has grown while the light was in transit, stretching not only space but the light itself. What began as searing ultraviolet radiation now reaches us as gentle microwaves, carrying within them the whisper of creation. Beyond the cosmic microwave background lies the unobservable universe, regions of space that exist but from which light will never reach us. These regions are not separate or different. They are simply beyond our horizon. The universe may be infinite, or it may curve back upon itself like the surface of a sphere. It may contain countless other regions with different histories, different densities, even different laws of physics. We cannot yet know. What we do know is that the observable universe is not the totality of existence. It is merely the part we can touch with our instruments and our minds. To gaze at the edge of the observable universe is to confront the limit of knowledge itself. It is the boundary between what can be seen and what must be imagined. The light from the beginning of time still washes over us, a soft glow from the birth of all things. It reminds us that we are creatures of that same creation, built from the same particles, governed by the same laws, and bound to the same fate. Beyond this horizon lies the realm of the unknown, where theory and imagination must venture in place of sight. And so, as we stand at the edge of everything visible, we ask again the question that has driven us from the solar system to the stars. What lies beyond? Is the universe infinite, or does it give way to something greater still? Are we part of one cosmos among many, or is this vast expanse all there is? These are not questions that can be answered by telescopes or equations alone. They are questions that touch the very nature of existence, the intersection of science and wonder. The next step beyond the observable universe takes us into the realm of theory, where physics meets philosophy and imagination dares to describe what lies outside space and time. There, beyond the cosmic horizon, we will confront the deepest possibilities of reality itself. At the edge of the observable universe, light itself falters. Beyond that horizon lies a domain we cannot see, not because it is hidden by distance, but because it exists beyond the reach of time. Yet human curiosity does not end where light ends. When observation fails, imagination guided by physics takes over. In this realm, the universe is no longer merely a collection of galaxies and stars. It becomes a question about existence itself. What lies beyond space and time? Is our cosmos the only one, or just one bubble in an endless sea of creation? One of the leading ideas that seeks to answer this question is the theory of the inflationary multiverse. It begins with the concept of cosmic inflation, that brief moment after the Big Bang when the universe expanded exponentially, faster than the speed of light. During that period, space itself stretched at a rate so extreme that a region smaller than an atom became large enough to encompass everything we can now see. According to this theory, inflation did not stop everywhere at once. Instead, it may have continued indefinitely in other regions, spawning countless bubble universes, each with its own physical laws and constants. Our observable universe would then be just one bubble among many, one patch in an eternal cosmic foam. Some bubbles might expand forever, while others collapse or spawn new ones in turn. This idea, called eternal inflation, transforms the cosmos into a vast and self-generating multiverse. In such a framework, every possible version of reality might exist somewhere. Universes where gravity is stronger or weaker, where stars never form, where time flows differently, or where matter itself is absent. The multiverse is not pure fantasy. It arises naturally from the mathematics of inflationary theory, supported by the same equations that explain the uniformity of the cosmic microwave background. Yet it is also deeply unsettling, because it challenges the idea of uniqueness. If infinite universes exist, then ours is not special, it is inevitable. The laws of physics we know might be local rules, valid only within our bubble, while others follow different patterns beyond our reach. Another framework that reaches beyond the boundaries of our universe is known as brain cosmology. In this picture, our entire universe exists as a four-dimensional surface, a brain, floating within a higher dimensional space called the bulk. The term brain comes from membrane, because in higher dimensional theories like string theory, the fundamental objects are not points but extended surfaces that can vibrate and interact. According to this idea, there could be countless other brains parallel to ours, each one representing a separate universe. These parallel brains could exist only a fraction of a millimeter away in another dimension, yet remain completely invisible to us because we are confined to our own brain. Gravity, however, might leak between them, which could explain why it is so much weaker than the other fundamental forces. Some cosmologists have even proposed that the Big Bang itself was caused by a collision between two brains in the higher dimensional bulk. Such an impact would have released immense energy, igniting a new universe, ours, while others continue to form elsewhere in the higher dimensional space. Quantum cosmology takes the question further still, suggesting that the universe has no definite beginning or end, but instead arises from the laws of quantum mechanics themselves. In quantum theory, particles can exist in many possible states simultaneously until they are observed, at which point the probability collapses into one outcome. Applied to the universe as a whole, this implies that space-time itself may exist in a superposition of possibilities. The cosmos we experience is just one realization of an underlying quantum state that contains all potential configurations of reality. In this view, the birth of the universe was not an explosion in space, but a transition from potentiality to existence. Before the Big Bang, there may have been no space, no time, no before or after, only a quantum field of probabilities. The universe emerged when that field fluctuated into being, collapsing into a specific form of space-time. This means that the question, what came before the Big Bang, may be meaningless, because before is a concept that requires time, and time itself began with that transition. Some models suggest that the universe may not be a one-time event at all. In cyclic cosmology, the universe expands, slows, and then contracts, collapsing into itself in a cosmic bounce that gives rise to a new expansion. In this endless cycle, creation and destruction alternate eternally, each universe giving birth to the next. This idea is found not only in modern physics, but also in ancient philosophy, from the Hindu concept of cosmic rebirth to the Stoic idea of eternal recurrence. If true, It means the universe is neither finite nor infinite, but self-renewing, an eternal heartbeat of creation. There are even more radical proposals. Some physicists have suggested that our universe could be a hologram, a three-dimensional projection of information encoded on a distant two-dimensional surface. This idea, known as the holographic principle, arises from studies of black holes, where information about matter that falls in seems to be stored on the event horizon rather than lost forever. If the same principle applies to the entire cosmos, then everything we experience, space, time, matter, could be a projection of fundamental data existing at the boundary of the universe. Another concept, called quantum loop gravity, suggests that space itself is made of discrete units, tiny loops woven together like fabric. In this model, the smoothness of space is an illusion, much like a photograph that appears continuous until seen under magnification. The universe would then have a smallest possible scale, a quantum of space, below which distance has no meaning. This idea challenges the traditional picture of infinite divisibility, hinting that even emptiness is quantized. All these theories, from inflationary bubbles to higher dimensional brains and quantum geometries, share a common theme. They remove the notion of a final edge. In every framework, the universe continues beyond what we can observe, whether as other universes, other dimensions, or deeper layers of reality. The cosmos, in this sense, has no boundary. It is infinite not necessarily in size, but in possibility. The search for what lies beyond the edge is not only scientific, but also philosophical. Each model forces us to confront questions about meaning and existence. If there are infinite universes, does ours matter less, or does each one matter infinitely? If reality is a projection, who or what encodes the information that defines it? If time itself began at the Big Bang, is the flow of time an illusion, a byproduct of consciousness observing change? These questions blur the boundary between physics and philosophy, yet they are unavoidable. The deeper we probe into the nature of the cosmos, the more we realize that the structure of reality is inseparable from the act of observation. The universe is not merely something we exist within, it is something we participate in. Every act of measurement, every thought, every life is part of the cosmic unfolding. The theories beyond the edge remind us that science does not end with certainty. It thrives on mystery, on the tension between what is known and what is possible. We may never cross the cosmic horizon, but through reason and imagination, we can glimpse what lies beyond it. The frontier of understanding expands with every question we dare to ask. And so, the journey outward continues, not through space now, but through idea and abstraction. Beyond the boundaries of our instruments lies the infinite frontier, where the universe and the mind become mirrors of one another. The next step is not to map new galaxies, but to comprehend the meaning of infinity itself. From the warmth of the sun to the silent gulf beyond the stars, we have followed the story of our cosmic home outward step by step. We began among the planets, where sunlight still holds sway. We passed through the heliopause, where the breath of the sun fades into the wind of the galaxy. We drifted through the Oort cloud, that invisible halo of frozen debris marking the sun's final gravitational reach. We crossed into the interstellar medium, journeyed among our neighboring stars, and then beyond the Milky Way into the vast architecture of galaxies, clusters, and filaments that make up the cosmic web. Finally, we reached the edge of the observable universe, where time itself becomes the final horizon. And yet, even there, we found that the story does not end. Beyond every boundary lies another. Beyond every horizon, another dawn. The infinite frontier is not a place, but a perspective. It is the realization that the universe has no final wall, no ultimate limit, only layers of understanding waiting to be revealed. The cosmos stretches outward into the unseen, and inward into the unknown depths of matter, energy, and consciousness. the same mystery that surrounds the stars also resides within every atom, every cell, every thought. The vastness outside mirrors the complexity within. When we look back toward the sun from the outer dark, we see a faint golden point, a small, trembling light suspended in endless blackness. That is home. Around it circle the planets, each carrying its own history, its own landscapes and storms and silences. From such a distance, Earth is almost invisible, yet from that fragile speck has come everything that asks questions, dreams, and seeks to understand. Every telescope, every equation, every act of wonder has arisen from that blue world orbiting an ordinary star. It is humbling to realize that in the cosmic scale, even galaxies are temporary. Stars are born, burn, and die. Galaxies collide and merge. Clusters drift apart as dark energy accelerates the expansion of space. Billions of years from now, the Milky Way and Andromeda will have fused into a single massive galaxy, surrounded by faint, dying stars. In the far future, most of the universe will grow cold and dark as the last starlight fades. Yet the atoms that make up everything we know, carbon, oxygen, iron, will endure, scattered across eternity. The universe may change form, but nothing truly vanishes. It only transforms. This truth connects the smallest and the largest scales. The carbon in our cells was forged in the heart of long-dead stars. The iron in our blood once lay in the core of supernovae that exploded billions of years ago. The oxygen we breathe was born in the same processes that shape the galaxies. We are not separate from the cosmos. We are its expression, condensed into awareness. To explore the universe is to explore ourselves. The infinite frontier also challenges the limits of human imagination. We are used to thinking of edges, borders, surfaces, endings, but the universe does not conform to such simplicity. The more deeply we study it, the less finite it becomes. At every scale, new mysteries emerge. The nature of dark matter, the behavior of black holes, the fabric of quantum spacetime, the possibility of other universes beyond our own. Each discovery opens another horizon, as if the cosmos continually unfolds to match the reach of our curiosity. Perhaps this is what it means to be part of a living universe, not one that ends, but one that evolves. Even if the stars go dark, even if space expands into emptiness, the story of existence continues in ways we cannot yet conceive. Some physicists imagine that in the deep future, quantum fluctuations may give rise to new bursts of creation, new universes budding from the cold ashes of the old. Others believe that information, the fundamental currency of reality, is never lost, and that every event, every life, every moment remains encoded in the structure of space-time itself. When we speak of infinity, we speak not of boundlessness alone, but of continuity. The cosmos is an unbroken thread, woven through all things, linking the beginning to the present, the microcosm to the macrocosm, the known to the unknowable. To touch that thread, even for an instant, is to sense the unity of all existence. The quiet truth that there is no real separation between what is and what perceives. In the end, the infinite frontier is both outward and inward. Outward, it stretches beyond the galaxies into realms that light will never reach. Inward, it dives into the subatomic world, where particles dissolve into probability and the structure of space itself becomes fluid. Somewhere between these two extremes, between the infinite vastness and the infinitesimal depth, lies the human mind, trying to comprehend it all. The story of our exploration began with simple questions. What lies beyond the planets? Where does the solar system end? Each answer led to another question, and each boundary we crossed revealed that there was no true edge, only a deeper mystery. Voyager 1, still sailing through interstellar space, continues to send its faint signal home, a whisper across billions of kilometers. On board is a golden record, inscribed with the sounds and images of Earth, a message to anyone or anything that might someday find it. That record carries a single profound statement. We were here. We wondered. We reached for the stars. Perhaps, somewhere in another galaxy, another civilization is asking the same questions. Perhaps they too look outward, tracing the light of distant suns, trying to find where everything ends. And perhaps they too will discover what we have begun to understand, that the universe has no true boundary, that every horizon conceals another, and that in seeking the edge, one always finds the infinite. So what lies beyond the solar system, beyond the heliopause and the Oort cloud, beyond the galaxies and the cosmic web? The answer is everything. Beyond the last whisper of sunlight lies all that has ever been and all that will ever be. Space without end, time without limit, the universe unfolding forever into itself. We began this journey searching for the edge of our home. What we found instead was that there is no edge, only the endless continuation of existence. The cosmos does not end where our sight fails. It continues in forms we have yet to imagine. And in that realization lies something profound. That even in the face of infinity, we are not insignificant. We are the way the universe comes to know itself, the moment when matter looks back at the stars and understands. We are not lost in the cosmos. We are the cosmos made conscious. We began by asking what lies beyond the solar system. The truth is, everything. Beyond the last breath of the sun, beyond the farthest comet, beyond the final spark of starlight, there lies a universe so vast that it may never end. And within that universe, we are not strangers. We are home.